So these are the solutions to the proportional reasoning. I think proportional reasoning is really important outside of physics as well as inside of physics. It helps you think about whether things make sense numerically in life, whether you're getting a good deal, bad deal, things like that. So um, I will get you a formula sheet before your first quiz, which has metric conversions on them, and I'll explain how to use that on, I think, the day before the quiz. I'll get that out. And that's something you can use all year on tests and quizzes. At any rate, here, metrics conversion, proportional reasoning, and again, I put some attachments with this that allow you to look at metric conversions. So if 100 centimeters is equivalent to 1 meter, how many centimeters are equivalent to 3 meters? Well, basically, I multiply through like this. So this is, I think, called dimensional analysis. Some people call it factor labeling. If you had things in chemistry, you've probably used stoichiometry to do things like this, but basically it's unit conversions. And the reason that those are important is because oftentimes there's multiple ways to measure things, and you want to have a good understanding of how they convert. And that's just, I think, going to be true your whole life, is you're going to have different things, different currencies, different measurements, different tools. So you want to be able to get good at that. So in this case, if this was our conversion factor, if we start off with 3 meters, I put 3 meters over 1. That lets me know that the 3 meters is in the numerator. Multiply by my conversion factor, which is 100 centimeters over 1 meter. How do I know it's this and not 1 meter over 100 centimeters? Because I want my meters units to cancel out. And if you know, notice I've shown that here. So I'm left only with centimeters, which is what I want, and that's 300 centimeters. The reverse process to go from centimeters to meters is down here. I have the same conversion factor, but meters is on top and centimeters is in the bottom, so centimeters cancels out. I'm left with meters. Hopefully it makes sense. I'm going to a smaller number, so I'm going from 45 to 0.45 because my meter is a larger unit of measure than a centimeter. So it's kind of like if you say that you're a cross-country runner and you're running a 5K, that's 5,000 meters. That's what that means, 5 kilometers. But it's 3.1 miles because a mile is a bigger unit than a kilometer, so you have fewer of them in the same race. So here we're doing conversion to get to meters. You could put things in scientific notation. I hope you know how to use that. If not, well, let me know. I think that was also part of the review that I'd gotten into, or that I attached with this. Grams to kilograms, same sort of thing, except I forgot to show how to cancel that out, so I'll do that now. Cancel, cancel. Nice. And those get canceled out. A mile is farther than a kilometer. Consider a fixed distance. So this is the example I gave with a cross-country race. But if you're looking at something like the diameter of a moon, the numerical value would be larger in kilometers because the unit is smaller. So more kilometers equals a fewer number of miles for the same measurement. I like this one. This is fun because we normally measure eggs in dozen, but chickens don't lay dozens of eggs every day. So let's say this is kind of a not very productive chicken that lays 1 egg every 3 days. How long would it take to lay 3 dozen eggs? So there's a couple ways you could do this. You might think that this would end up being 12 days if you did 36 divided by 3. But the thing is here, if you look at this, you could recognize that you need 36 eggs and you need X days to do that. And so therefore, we've got 1 egg for every 3 days is equal to 36 eggs over X number of days. So you could do it like that. The other way you could do this is you could say, I'm going to move this down here, maybe. You could say you need 36 eggs times 3 days per 1 egg. And that equals 108 days. So that's kind of the same method we used up here in terms of the factor labeling or the dimensional analysis. Did it a little differently right here. Okay. So this one I probably should have left more space for me, but in your Google Doc you should have been able to write that down. Again, if you don't want to show how it cancels out, that's okay. But you should definitely show or list the logic for how to convert those. So I've got 1.25 euros per 1 liter, which is quite expensive. 3.78 liters per gallon, $1 over 0.84 euros. And once again, if I look, euros on top, euros on bottom, liters on top, dollars on top, gallons are on bottom. I'm left with dollars per gallon. So in Germany, the cost of fuel right now is about $5.62 per gallon. So it makes sense why they have such fuel efficient cars over there. In the US, if we have an average cost of around $2.19 per gallon, and we're multiplying by sorry, the floor did its burping, which is weird, and it sounds like it's a bad plumbing problem. So I muted there for a moment. At any rate, $2.19 per gallon times the gallon to liter conversion. Again, gallons are on bottom, so we want to have that on top here. And then we're going to convert dollars to euros, so we have euros on top, dollars on the bottom. We end up with euros on top, liters on the bottom. Everything else has canceled out. So that's a little less than half a euro per liter. And they would be ecstatic to have that cost. So that would be good. That seems a little off, though. I'm trying to think about that. 0.84 euros per dollar, 2.19 a gallon. Nah, I guess that's about right. I always like to see if things make sense in my brain. So I guess that does make sense. This graphical method summary, again, I included it with this assignment, but it should be something you've now got taped in the front of your composition book. It won't be on your formula sheet, so if you want to write some of those things on your formula sheet, that's fine, but my hope is that you'll learn those and know those relationships pretty well. So if you have something y equals kx and x is halved, then I would say that y is halved also. So I should have put y there. I'm going to change this to green. Y. I'm going to make it bigger. Not bold it. White background. Nope, that's not what I want. White background. So there we go, y is halved. So the way I like to think about these is I like to think about the initial conditions where you pick the simplest numbers you can. The simplest number I know is 1. So if I look at this equation, let's say we start off with constant of 1, x value of 1, then y would be 1. 1 equals 1 times 1. Now, if we halve the x value, I would get that y is equal to 1 times 1 half, so y is 1 half. Same sort of thing over here. This is my general formula. So I could say 1 equals 1 divided by 1. But now, if x is tripled, y equals 1 divided by 3. So y is 1/3 as much. Here, y equals k over x squared, and x is doubled. So initially 1 over 1 divided by, or 1 equals 1 divided by 1 squared. So now y equals 1 over 2 squared, since x was doubled. Well, 2 squared is 4, so y is 1/4 what it was before. Similarly here, y would be equal to 9. So this is actually a super useful thing to be able to do. Allows you to think just proportionally. I had a trick one with number 9. So these are the different relationships, again, on your graphical methods handout. So this would be a direct proportion, meaning they both start at 0, and as x increases, y increases by the same amount each time. So if x is 1, y is 3. If x is 2, y is 6. If x is 5, y is 15. For every single number that x increases, y increases by 3. This is also a direct proportion. This one, however, is an exponential proportion. So we don't know what the constant a is, but if x is 1, y is equal to a times 1. if x is 2, y is equal to a times 2 squared, which is 4a. So that's exponential. This is an inverse relationship. For E, G is also an inverse relationship. Y is a direct proportion. This one's tricky, not among the choices I gave you, but we will see this relationship this year in two separate cases. This is actually an inverse squared proportion, meaning if x doubles, y decreases by a factor of 4, so it becomes 1/4 as large as it was before. So that's tricky. Hopefully this graph you can use to recognize some things, again from your graphical method summary. B and E both start from 0, and they're straight lines, so those are both direct proportions. This is a linear proportion for D because it does not start from 0, meaning if I go from, say, x equals 1 to x equals 2, it's not the same increase as if I go from x equals 2 to x equals 3 over here for the y-axis. Or 0 to 1 is not the same increase as from 1 to 2. I guess I should say it that way. So it's a linear relationship, but because there's a y-intercept, it's not a directly proportional relationship. So key thing there, y-intercept. A is an inverse proportion. It's the only one we have where when one variable goes up, the other goes down in a manner that's consistent with that graphical method summary. So basically this would equal 1 over x, something like that. Y equals 1 over x, that is, or y equals a constant over x. So essentially if x triples, y is 1/3 as much. If x quadruples, y is 1/4 as much. So which relationships are exponential? That's C. And F isn't shown by any of these. So it is definitely a negative relationship, meaning when the x variable increases, the y variable decreases, but it's not an inverse relationship. An inverse relationship is a very specific type of relationship where when one variable increases, the other decreases. So hopefully these help, and again, hopefully they help you prepare for your quiz.